Okay, for this next segment, I just want to be clear on where I'm measuring my circuit, and I didn't show the connections on the car. It was too difficult to show where we were connected. On the bank 1 sensor, again, we were connected. One channel was connected to that signal wire, and one channel was connected to this signal wire. So our AF positive and our AF negative. And we were not focused on the heater circuit on this at all. None of this stuff we were doing the heater. And then I was also on my bank 2 sensor, which we said was our working sensor. I was connected here, and I was connected here using voltage scales. For this next part, we're going to focus on our bank 2 because this is our working circuit. And I'm going to keep these connected, and what I'm going to do is connect an amp probe around the blue wire first, see if we get an amperage reading off of that, and then I'll do the same thing with the black and white wire, and we'll compare it to the scan tool still when we have our voltage changes, see if we see some type of current flow change. Okay, so we have our amp probe connected to our bank 2 sensor, and I needed another channel, so I unplugged the yellow trace, which was on the bank 1 sensor positive, is now my bank 2 sensor current. And what we see is basically a little noise in the circuit, which is pretty typical in these low amperage scales. I'm on a 1 amp scale. My live amperage is basically 0. It's the same as it was when I had it disconnected. Do some snap throttle tests. As you do the snap throttle, you saw the voltage on bank 2. I saw a 4 volt at one point, I saw a 2 volt at another point, and I did not see the current change on that wire. Let me go to the other one. I don't think it's going to matter. And this is the other wire. Got to do the same thing. This will be our sensor negative wire now. See the voltage changes. We're not seeing the current flow. So I guess what this is telling me is this is in a microamp range, and I do not have sensitive enough of an amp probe to be able to read this. I don't know if I can maybe AC couple this and go on a lower scale, but I think we're going to have way too much noise if we try to do that. I just think that I've reached my limit of what I can do as far as testing the sensor with the equipment I have. I think we're comfortable with our voltage readings at the sensor, knowing our harness is good. I think we're comfortable with putting a sensor in it at this point. I think there's something else to consider is these are not all the same. I've seen varying voltage levels on different cars, and don't forget we got 5 wire and 7 wire ones too. This is a 4 wire. We're going to put a upstream bank 1 sensor 1 O2 in it. I'll get you an after shot of that so everybody's comfortable we made the right call. Okay, I have some final thoughts on this car. That number 1, voltage is inverted on this. When we look at the scan tool, and that's on this model, again, this is a 4 wire wideband O2, that voltage is inverted. So by inverted, I'm saying that instead of low voltage being lean, lower voltage is rich and higher voltage is lean. So it is opposite of what we would look for on a conventional narrowband zirconia O2. Something else that we can pick out of this case study is that scan data is required for proper troubleshooting. To know what the computer is seeing on this sensor circuit, we need to have scan data to do it. You saw as we were adding propane, as we were snapping the throttle, and again we were focused on our bank 2 where we had our voltage numbers changing, matching mixture changes. Scan data, it never changed on the scope. Voltage stayed the same. So we need scan data. So now for the scope testing part, our scope voltage readings, they don't really help us interpret what the sensor's doing, if the sensor's even functional. What we saw with a non-functional O2 on the green and the yellow trace, which is bank 1, was really pretty much the same as the Bank 2 functional O2 or air fuel sensor. So scope data, live scope measurements wasn't very helpful. However, I think there's some value to the scope measurement when it comes to the wiring problems. For wiring problems, what the manufacturer flowchart wants you to do is it wants you to do resistance checks. And you guys all know how I feel about doing resistance checks. There are times to do them. Let's not totally discredit the ohm meter. There's times it's necessary. But to do an ohm check here would involve removing the computer, pulling it down out of the dash, finding the wires, disconnecting the sensor, and then ohming the wires for opens and shorts. And that's a pretty long process. I wouldn't be surprised if that took you 45 minutes by itself to do that. And I think the voltage test that we did on this car, and again, this is this car, we'll have to do some more of these and build a database, but I think the voltage test that we did for this car, having this Bank 2 sensor unplugged, again, a known good circuit, I unplugged the sensor and you saw that we had voltage of 3.3 and 3.0, exactly what the flowchart said we should have. Where's that voltage coming from? It's coming from the computer. So how's the wiring between the computer and the sensor if you do that check? Instead of ohming the circuit, can we do that? And I think we can. So I like that. I like the scope voltage checks for that. Can we apply that across the board? I can't answer that yet. But I like where we're at with that, and I think I'm going to adopt that. So I don't want to totally discredit voltage checks at the wideband sensor, even though the flowchart said specifically, and what we saw, that it is impossible to confirm air fuel sensor output voltage without using a scan tool. That doesn't mean we can't check it. Open short circuit tests, I'm saying we're good. Something else that we can pull from this. Our short-term and long-term fuel trim diagnosis is really no different. When we started with this, we had, I don't have the full data list up here, I still have my scope and my scan tool data up top, but when we were looking at this data list, we had fuel trim numbers that were pegged rich. And we said to ourselves, this thing's running either lean or we have an O2 problem, and we put propane in it, richening the mixture. It didn't respond. So we were able to do the same tests we did on conventional O2 sensors. And we were able to say that this thing had a sensor problem, not a mixture problem. How valuable was that? Well, when you go through this flowchart after, now think about this, after, this is what the manufacturer wants you to do, after checking the sensor voltage on the scan tool and doing some tests and then test drive, they want you to do your resistance checks next, which would be disconnect the computer, disconnect the sensor, ohm the circuit. And then after that, and only after you verified wiring integrity, then they start having you check for lean conditions. I'm reading step 5 and step 6. Ensure oil dipstick, oil cap, oil filler cap, PCV, air induction components are intact. Repair as necessary. Check fuel pressure. Make sure your injectors are working properly. Do flow tests on the injectors. And only after all of that, you've checked your wiring, you've checked all of your fuel components, do they tell you to replace the defective, if the problem still persists, to replace the defective sensor. Well, what we did by adding propane to this, and that our fuel trim did not react and it stayed positive, and the sensor didn't react and it stayed high, indicating a lean condition, says that the sensor, or says the fuel system's fine. So why are we even doing those other steps? Gotta love the flow charts, guys. Short-term, long-term fuel trim diagnosis, again, we can handle those. No different than we do any other oxygen sensor. So I guess the last part, the open-ended part that I'm not comfortable with, would be how does the computer react? How does it actually read this number right here? We know that that number is not either one of these. This 3.3, I know you're looking at that saying, well, that blue trace, that 3.3 is the same 3.3 as right there. You're right, but as we drove this mixture rich and lean on the scan tool, on the car, watching the scan tool, watching this number at times go to 4 volts, at other times go to 2.8 volts. That never moved. So what we know is that voltage right there is not either one of these two. It's going to be a comparison of those two. How's the computer comparing those two circuits? I believe it's using current flow. I have read on these that it is current flow, that the computer monitors the current flow on a wideband sensor to determine the ratio. And I think this is a pretty good view of that, or I think that seeing this one change and this one not, how can there be a change up here if it wasn't current flow? It has to be current flow. And I wish I could say that with confidence where I've actually measured one. I don't have the equipment to. I have some great equipment, but the amp probes and the scales I have aren't sensitive enough. I even tried using the lowest settings I have, and I think in this part I didn't film, I actually switched to a multimeter too, and I had 6 milliamps, but that was just the zeroing of the probe, and I had 0 changes on this. So what kind of amperage are we talking about? We're talking about microamps, and I don't have the equipment to measure microamps. This would be the only component on the car that I would ever need to measure a microamp. And again, I apologize if I'm giving bad information here. This is just what I'm seeing. I think you guys can maybe see why that there's a lot of need in the field for more wideband stuff. There's a lot of confusion. There's a lot of guesswork maybe that is involved here, and that we don't have the right equipment. But let's think about this for a second. Is there a diagnostic advantage to knowing what the current flow is? If your sensor signal is off on the scan tool, if this number's off like this one was, and we know that the sensor is either malfunctioning, or the wiring is malfunctioning, or the computer is malfunctioning, those were our 3 choices, and we do our voltage checks and we find the right voltage values, I think we have enough information to put a sensor in the car. Do we have enough information to identify rich and lean conditions? Yes. Lean is higher voltage, rich is lower voltage. Can we still use the scan data to do, say, fuel delivery tests and take the car for a test drive, wide open throttle, make sure the car's running rich, to identify, say, low fuel pressure problems and dirty mass airflow sensors and things like that? I think yes, we can still do that. So what would be the diagnostic advantage of putting an amp probe on a wideband sensor to actually see the rich lean changes, other than looking at the scan tool and making sure that the voltage is where it needs to be? I really don't see the necessity to do that. I think it would be fun for theory purposes. Am I going to go run out and buy some extra tools? No, I'm not. Would be curious to hear some feedback on this, and maybe what some of you guys are doing out there on these. Hopefully you like that. Hopefully we learned something, and I have to tell you guys, look for more. I'm going to do some more of this on some other wideband sensors as I encounter them. I will shoot some more videos, and down the road we'll get some more info in the ebook too on some wideband stuff. Okay, we just installed this Bank 1 Sensor 1 air fuel sensor, and we did have the car running before this shot, so I apologize that we didn't get the initial first view of what the data looks like. I'm gonna go ahead and start it. And we're sitting inside the car this time, so the sound is a little muffled. But looking at our data parameters, we'll wait till this goes into closed loop. Oh, I don't have my loop status up here, do I? Let's get that in here. Okay, we just dropped into closed loop. Short-term fuel trim on Bank 1, you see, is 0.8, basically 0. Long-term, 0. I am in closed loop. You see our air fuel readings, 3.2 volts on both sides. 3.3, that's where the material or the book say we should be. So this is at idle. And if you remember how lean we were before, it was like 50-some% on the long term and in the upper teens on the short term. So I remember being around 60% total fuel trim. And so what that means is replacing that sensor. That is a fix. But what we want to do with this is we don't want to let it go just yet. We did have a P1130 code too. And of course, normally you have a bad sensor like we had, you're going to take care of both a lean code and the sensor code. But I want to check this at different RPMs. So I'm at idle. It looks good at idle. I don't see an issue. A little bit more positive on bank 2, but that's not an issue. We're still in a good range. I'm going to hold my RPM up and see where we're at. Just want to make sure we're not running lean at different RPMs. And I got to tell you, at 1600, this bank 2, I don't like the short term. And we did clear the memory, so we're not going to have really long-term numbers to go by. Let's really focus on the short term because we did clear memory on this. Go a little bit higher. And now both banks are lean. 2300, 2400. Now they just went to a normal range there. We're going negative now. That's kind of strange. Go a little bit higher. There's 3000 RPM, and you see my long term has corrected. We're 9%. Do total trim here and add these together is what you want to do. So there's 10% on that one. There's 6 or 7%. Not too bad. Back down to 2000. That looks pretty good at $2,000. I didn't like that initial 14% or so we had. Are we getting some negative fuel trim numbers on occasion? One of the things that can cause that is, you know, how long has this thing's been running rich? We had a faulty O2 lying to the computer, telling the computer that this mixture was lean and the computer was richening the one bank severely. And what you're gonna have is fuel contamination of the oil PCV system, get a little cylinder wash. And really with these negative fuel trim numbers that we're seeing, I think an oil change is in order here on this car. Anytime you have a rich condition for any period of time, you always want to recommend an oil change. My main concern was that P1130 and making sure that was gone. I don't like that right there. Did you see that 19% at like 2300? And just to shorten this video is going to be really long as it is. We're going to do a quick visual inspection on this mass airflow. My suspicions would be that this mass airflow is a little bit contaminated, and that can contribute to these negative fuel trim numbers at idle. We did fix this air-fuel ratio issue, no question about it, but we have another problem here, and I really would like to address these fuel trim numbers. Oil change for sure, but let's look at this mass airflow. Okay, again, just in order to save time, I'm not going to do electrical checks on this mass airflow. I've shown how to do it. This is a analog type mass airflow. It's a 5-pin. This is just like the Subaru one we did. This is a Lexus model, same as Toyota, same as the Subaru. You got your intake air temp sensor here on the side. You got your hot and your cold wire down inside of this unit. And I've had some questions on the last one about the plastic and worried about hurting the plastic with brake clean. And this is not a regular type of plastic, and you're not going to hurt it with cleaner. I wouldn't want the cleaner up in this area. Of course, stay away from that. You're only using a little bit down in this area. And I got some questions too on how I clean them, so I'm going to get a lot of crap for this, but I'm going to show it anyway. And well, first of all, let's see if I can get you a shot of this. The last one, after editing the video, it really was hard to see, and I'm going to use the camera light now instead of my flashlight, and hopefully we can see these contaminants that are on this hot wire, which is the top one, I believe, is the hot wire. The bottom one would be the cold wire. I think that might be the shot right there that shows it. See if I go a little further. You see some contaminants on that, and it looks like that resistor is a little bit tweaked already too. Like maybe someone has cleaned this in the past and they got a little bit too rough with it and pushed down on that. It shouldn't affect it too much as long as you don't push too hard. I mean, you definitely don't want to damage those. And what I'm going to do to clean it is I'm going to scrape it with my pocket screwdriver. And I know I'm going to get some crap for this, but you know, whatever. I've been doing it for years. I didn't want to admit it in the last one. I'm not recommending that you clean mass airflow sensors with a pocket screwdriver. And I want you guys to know that I'm not pushing hard at all on this. I'm just dragging it across the resistor and pulling the crap off of it. And I still use a little bit of spray cleaner when I'm done, but that's what I'm going to do. I'm going to have to zoom out to show that. And you know, I'm having second thoughts about even showing this, but whatever. All right, I think just for experiment purposes, I'm not even going to use any kind of cleaner here. I'm just going to put this back in and see what the result is. After doing what I just did, I'll get you a shot back on it again, see if you see the difference in the resistor. You know, I'm kind of laughing as I'm filming this on what you guys might think about how I just cleaned this. I'm not suggesting that this is ideal. But if you don't have a brush that's small enough to get down in there, and you don't want to use a big fat brush where you can't see what you're touching and you can't judge the amount of tension that you're putting on these resistors, we don't want to move them, we don't want to bend them. I just cleaned that with my pocket screwdriver. Let's put it back in the car and see what our fuel trim numbers look like. All right, this is our after data of our pocket screwdriver cleaning mass airflow sensor, and we're gonna start it, see what we got. All right, let's get our idle shot first. Total trim, bank 2, is going to be pretty good. Total trim on bank 1 also looks pretty good. Again, this thing's got wiped out memory, so we're going to have a little bit of conflicting data at times where short term is positive, long term's at 0, and you're seeing that. Eventually that number here is going to be over here, and this number will be 0 over here. It was right around 2100, 19 to 2100. We had a almost 20% addition of fuel before we cleaned this mass airflow. There's 1800. The multi-tool is what I call it. The pocket screwdriver. You can do everything with a pocket screwdriver. It's a must-have tool. These numbers look pretty good. I feel pretty comfortable letting this car go. I don't mind a 5% and a 7%. By the way, this car has 200,000 miles on it. Probably should have mentioned that. And I'm still going to recommend an oil change, especially for that right there. These negative numbers initially on the decel, but they look pretty good right now. It was like right after letting my foot off the gas pedal. We'll definitely tell them to do an oil change, but I'm pretty sure that took care of the rest of our lean conditions, cleaning that mass airflow. So another technique, I know I'm going to get hell for it, but this car is a fix. I guess one last shot on our air fuel sensors. If you guys want to see them, make sure we're fixed there. Get those back in the screen, and you see we're at 3.3 volts, 3.2 on bank 1, 3.3, 3.2 on bank 2. That's exactly what we want to see. A little bit of snap throttle where we were getting those changes before. You snap it, voltage should drop, and if you let off the throttle, voltage will rise. Let's snap throttle rich, voltage should drop. Let off the throttle, fuel cut, voltage rises. That's a good looking sensor now. That is a fix. Hope you guys like it.